Carrier lines provide dedicated, secure point-to-point connections between two fixed subscriber locations. Carrier lines are reliable because the connection is always active, and they provide optimal performance because the full bandwidth of the connection is always available. The primary disadvantage of carrier lines is cost. They typically cost more than other types of WAN connections, such as Integrated Services Digital Network, or ISDN, and Digital Subscriber Line, or DSL. Furthermore, the cost of a carrier line increases substantially if that line passes through more than one public carrier network, because each carrier charges for the dedicated circuit it provides. Carrier WAN connections are ideal for companies that must exchange a high volume of data and require constant access. For example, a company may need to share large files between a limited number of sites, and the information may be highly confidential, requiring a secure connection. Companies may also purchase a carrier WAN connection if they need high bandwidth for the Internet, their intranet, and email. A carrier WAN connection may also be required for private branch exchange or PBX applications that use a large number of channels and need drop-insert functionality. Voice and data traffic carried on a single carrier line, government, military, and corporate secure information exchange, Internet Service Provider, or ISP services. This slide shows the general characteristics of an end-to-end carrier line WAN connection. A carrier line WAN connection provides a permanent, dedicated, point-to-point, fixed bandwidth link between two sites. Unless the service provider changes the path, the data sent between the two endpoints in a carrier line WAN connection always flows along the same physical path. However, having a dedicated path does not mean that the full capacity of each copper or fiber cable used in the physical path is reserved for that single connection. For example, traffic from multiple T1 connections might be multiplexed over one physical path on a higher speed link. Nevertheless, the bandwidth for each connection is guaranteed across all parts of the path because each connection is allocated dedicated time slots end to end. If there is no traffic to transmit, the time slots for that connection go unused. T1 and T3 carrier lines are used primarily in Canada and the United States. In Europe and other sector locations that follow the telecommunications standardization sector of the International Telecommunication Union, or ITU-T standards, the comparable dedicated high-speed WAN connections are E1 and E3 carrier lines. J1 and J3 carrier lines were defined for use in Japan. As stated earlier, the DSU translates the signal in both directions. The DSU converts signals from data terminal equipment, or DTE, on the subscriber's LAN to the format required on the WAN connection and forwards the formatted signal to the CSU. The DSU also converts formatted signals from the WAN connection from the CSU to LAN or DTE signals and forwards them to the subscriber's WAN router. Finally, the DSU provides the capability to test the connection between itself and the LAN. The WAN connection begins at the CSU. CSUs vary, but all CSUs provide at least the following basic functionality. The CSU contains the last signal regenerator on the public carrier network. In other words, the CSU acts as the final repeater from the WAN side. This signal regenerator presents the DSU with a clean WAN signal for conversion to the DTE signal format and forwarding to the WAN router. The WAN signal used depends on the type of WAN connection. For example, T1 WAN connections use DS1, E1 WAN connections use E1, and J1 WAN connections use J1. For more information about signaling hierarchies, refer back to Module 1. The CSU also contains a mechanism for putting the physical line into loopback mode for line testing between itself and the public carrier's CO. In addition, the CSU enables configuration of line build-out. You can control the waveform to compensate for signal attenuation on the line. Some repeaters and other equipment are built so that they expect a specific amount of signal attenuation. They will not work unless that level of attenuation is present. The CSU enables control of attenuation to ensure that all components on the end-to-end connection perform properly. The CSU monitors the signal from itself to the public carrier CO to detect signal pattern violations and loss of signal. When problems do occur, the CSU might perform autocorrection or generate an alarm, depending on its capabilities and the problem detected. You need only be familiar with the general functions of the CSU-DSU. The public carrier normally configures it. If the public carrier does not configure it, the public carrier must provide the necessary configuration information, such as the number of decibels of attenuation required for proper line build-out. WAN routers have two basic functions. First, they must determine whether traffic coming from any one of multiple sources on the connected LAN is intended for transmission across the WAN. Second, WAN routers must transmit this traffic. In addition to these basic functions, WAN routers must support one or more types of WAN connections, including carrier lines, ISDN, and DSL. WAN routers must also support one or more data link layer protocols, such as point-to-point protocol or PPP, multi-link PPP or MP, frame relay, multi-link frame relay or MFR, and others. Today's WAN routers offer a number of other capabilities. For example, many WAN routers include a built-in multiplexer. A multiplexer collects data and frames it into channels according to the speed or number of channels the subscriber purchased. The multiplexer combines any number of digital signal 0 or DS0, E0, or J0 channels into one serial data stream. WAN routers may also support add-drop multiplexing, enabling you to mix voice and data channels or non-consecutive channels. WAN routers might also have a built-in CSU-DSU. Built-in CSU-DSUs are somewhat easier to manage than standalone CSU-DSUs. They are also cheaper. For example, V.35 and X.21 cables, which connect a standalone CSU-DSU to the WAN router, are expensive. On the other hand, standalone CSU-DSUs are usually easier to monitor and troubleshoot. WAN routers might include security capabilities such as Virtual Private Network or VPN support, Virtual LAN or VLAN support for tunneling protocols such as Generic Routing Encapsulation or GRE, support for the security components of tunneling protocols such as Internet Protocol Security or IPsec, and even firewall capabilities. These capabilities are treated in other modules in this course. Typically, all of these capabilities are provided on interchangeable cards that are inserted into card slots in the WAN router. Many WAN routers also support remote monitoring or RMON, which enables you to monitor and control the WAN router regardless of your physical location. RMON defines a set of statistics and functions that are exchanged between RMON probes and RMON agents. RMON probes provide real-time information regarding the status of the device, network performance, network events, failure or error conditions, and other vital statistics. RMON agents, also called RMON consoles or RMON management consoles, present this information in a meaningful way for use in managing network operation. T-carrier WAN connections are based on the American National Standards Institute or ANSI T1.102 and T1.107 specifications. A T1 WAN connection provides 24 64 kilobits per second DS0 channels for a total of 1.544 megabits per second in bandwidth. A full T1 connection uses all 24 DS0s. Fractional T1 connections, which use fewer than 24 DS0s, are also available. The channels in a T1 connection can be used for voice traffic, data traffic, or a combination of the two, but all traffic moving through the connection is in digital form. In North America, a subscriber's site is connected to the CO of a local exchange carrier or LEC that provides the T1 WAN connection. T1 WAN connections can also be created through multiple LECs and inter-exchange carriers or IXCs as needed to link two subscribers' premises together. As mentioned earlier, the connection between a subscriber's premises and the CO is called the local loop. Most T1 local loops use two pairs of Category 3 or Cat3 or Cat5 UTP cable with 120 ohm 22 gauge wire. However, some older T1 installations use 2 pairs of Cat2 UTP with 100 ohm 24 gauge wire, which is adequate for full T1 applications. A T1 WAN connection creates a point-to-point connection between 2 locations, and a CSU-DSU is required at each end of the connection. You must configure the CSU-DSU to use the same line encoding scheme as the public carrier providing the T1 connection. As discussed in Module 1, both alternate mark inversion, or AMI, and bipolar 8 zero substitution, or B8ZS, encoding schemes are used in T-carrier WAN connections. Prior to configuring the CSU-DSU, you will need to contact the public carrier providing the T1 connection to determine which encoding scheme is appropriate. You must also configure the WAN routers to use a data link layer protocol that supports point-to-point connections. The default protocol is PPP. High-level data link control, or HDLC, MP, and frame relay can also be used. PPP, HDLC, and MP are discussed in detail in Module 2. Frame relay is discussed in Module 6. As this slide shows, a T1 CSU-DSU can be a standalone unit, or it can be built into a WAN router. The physical connections are different for each. A standalone CSU-DSU connects to the WAN router's V.35 serial interface with an external V.35 cable. It has an integrated RJ48C jack for connecting to the T1 RJ48X wall jack with Cat3 or higher UTP. A CSU-DSU that is integrated into a WAN router still uses a V.35 serial interface to communicate with the router, but it does not require the external V.35 cable. The connection between the CSU-DSU and the T1 jack is identical to a standalone router, RJ48C to RJ48X with twisted pair cable. As the slide shows, T1 WAN connections are terminated with RJ48X jacks. These jacks contain automatic cross-connect pins that provide automatic loopback. Automatic loopback keeps the T1 WAN connection operational on the public carrier's side of the circuit in the event the subscriber's end is disconnected. As discussed in Module 1, E-carrier lines are based on the ITU-T G.703 specification. An E1 WAN connection provides 32 64 kilobits per second DS0 channels with 2.048 megabits per second in total bandwidth. The bandwidth of an E1 WAN connection is greater than that of a T1 WAN connection for 2 reasons. First, more channels are provisioned for an E1 WAN connection. Second, all framing and synchronization functions are performed exclusively in 2 E0 channels, making the full bandwidth of the remaining 30 E0 channels available for data transport. A full E1 carrier WAN connection uses all 30 E0s. Fractional E1 carrier WAN connections, which use fewer than 30 channels, are also available. The channels in an E1 WAN connection can be used for voice traffic, data traffic, or a combination of the two, but all traffic moving through the connection is in digital form. In regions that support the G.703 specification, a subscriber's site is connected directly to the Public Telephone and Telegraph, or PTT company, that provides the E1 WAN connection. Depending on the location of the subscriber, the local loop transmission media will be either 2 twisted pair of Cat3 or Cat5 UTP with 120 ohm 22 gauge wire, or 2 unbalanced coaxial cables of 75 ohm solid core RG59. An E1 WAN connection creates a point-to-point connection between 2 locations, and a CSU-DSU is required at each end of the connection. With an E1 WAN connection, however, the CSU and DSU are usually separate devices. The CSU is owned and operated by the PTT and is installed on the PTT's side of the DMARC. The DSU, on the other hand, is owned and operated by the subscriber and is part of the equipment on the subscriber side of the DMARC. You must configure the DSU to use the same line encoding scheme as the PTT providing the E1 WAN connection. As discussed in Module 1, AMI and high-density bipolar of order 3 or HDB3 encoding schemes are both used in E1 WAN connections. Prior to configuring the DSU, you will need to contact the PTT to determine which line encoding scheme is appropriate. As with T1 WAN connections, you will also need to configure the WAN routers to use a data link layer protocol that supports point-to-point connections. As before, the default protocol is PPP, but HDLC, MP, and frame relay can also be used. In E1 WAN connections, the DSU can be a standalone device or it can be built into a router. The physical connections are different for each. As this slide shows, a standalone DSU connects to the X.21 serial interface of a WAN router with an external X.21 cable. The DSU is then connected to the E1 RJ48 wall jack with Cat3 or higher UTP. An integrated DSU does not require the external X.21 cable, but uses the same Cat3 UTP to connect to the E1 RJ48 wall jack. The CSU is owned and operated by the PTT and is located on the PTT side of the DMARC. J-carrier WAN connections are a closely related variant of T-carrier WAN connections. Like T1 WAN connections, J1 WAN connections provide a transmission speed of 1.544 megabits per second and 24 channels. J1 WAN connections also perform all signaling and control functions in band. However, J1 WAN connections use a slightly different framing format for signal transport than T1 WAN connections. J1 WAN connections use the J1 signaling format rather than DS1. PTTs in Japan use the J1 standard for voice, not data. For data, these PTTs use the T1 and less frequently the E1 standard. For example, Nippon Telegraph and Telephone, or NTT, the largest PTT in Japan, offers a DS3 connection with a transmission speed of 44.736 megabits per second. Likewise, KVH, another PTT company in Japan, offers both a T1 and a DS3 option. Many PTTs in Japan are using the T1 standard because they are delivering WAN connections over fiber optic networks that support the Synchronous Optical Network or SONET standard. SONET is the standard adopted by the United States and Canada for fiber optic networks. Not surprisingly, SONET provides backward compatibility for T-carrier lines. SONET is described in more depth later in this module. In addition to offering T1 or T3 WAN connections, PTTs in Japan offer even faster connections over fiber optic networks. For example, KVH offers a 622 megabits per second SONET-based connection and a 2.4 gigabits per second SONET-based connection. The signaling hierarchy that forms the basis of these connections is explained later in this module. PTTs in Japan also offer leased lines over Ethernet and asynchronous transfer mode, or ATM networks. SONET-based fiber optic networks require different equipment than standard carrier lines. Instead of a CSU-DSU, an add-drop multiplexer, or ADM, is used to establish the connection and the signaling between the customer's premises and the CO. In addition, a fiber termination box is required between the twisted pair cabling used on the customer's network and the fiber optic network. When a customer signs up for a leased line with the PTT, the agreement may include rental of a WAN router. However, the customer should be able to purchase and use any WAN router that supports the T1 standard, but should double-check with the PTT to ensure that WAN router is supported. Some WAN routers may also require a separate card that supports an external CSU-DSU, which is, in this case, an ADM. T3 carrier lines are based on the ANSI T1.102 and T1.107 specifications and use the DSX3 interface and DS3 signaling specifications defined by the DSX hierarchy. Public carriers deliver T3 carrier WAN connections as either a channelized or a non-channelized service. Channelized T3 delivers a total of 672 DS0 channels, 28 DS1 channels, and provides 44.736 megabits per second in nominal bandwidth. Channelized T3 uses DS3 signaling, which is multiplexed in a two-step process. First, a total of 28 DS1 signals are multiplexed into 7 DS2 signals. each of which contains 4 DS1 signals. Second, the 7 DS2 signals are multiplexed into 1 DS3 signal. In channelized T3, the public carrier performs all multiplexing. In contrast, non-channelized T3 delivers a single DS3 with no DS0, DS1, or DS2 multiplexing. It provides 44.2 megabits per second in available bandwidth. 1.997 megabits per second of the nominal T3 bandwidth is used for in-band framing control and signal synchronization in a process referred to as bit stuffing. In non-channelized T3, the subscriber is responsible for multiplexing if that subscriber wants to split the T3 into multiple channels. Both channelized T3 and non-channelized T3 require one of the following for the local loop: 75 ohm solid core RG59 coaxial cable, or single-mode or multi-mode fiber optic cable. T3 WAN connections use BNC connectors for coaxial cable and SC or ST connectors for fiber optic cable. T3 WAN connections also require a CSU-DSU at each subscriber's location. You must configure the CSU-DSU to use B8ZS line encoding. You will also need to configure the CSU-DSU for channelized or non-channelized T3, depending on which one you are implementing. As with the T1 and E1 connections, you must configure the WAN routers to use a data link layer protocol that supports point-to-point connections. The default protocol is PPP, but HDLC, MP, and frame relay can also be used. As this slide shows, a T3 CSU-DSU can be a standalone device, or it can be built into the router. The physical connections are different for each. A standalone T3 CSU-DSU is connected to the WAN router's high-speed serial interface, or HSI, with an external HSI cable. HSI uses a sub-miniature 50-pin male connector that is identical to a small computer systems interface 2 or SCSI 2 connector. The HSI signaling interface is a subset of the SCSI 2 specification. HSI provides a synchronous serial transmission rate of 52 megabits per second and supports both channelized and non-channelized T3. HSI also supports the 52 megabits per second transmission rate of Optical Carrier 1 or OC1. OC1 is the base multiple of SONET and the Synchronous Digital Hierarchy or SDH, which, like SONET, is discussed in depth later in this module. A standalone T3 CSU-DSU can be connected to the T3 WAN connection in one of two ways: a 75 ohm solid core RG59 coaxial cable with BNC connectors, 2 fiber optic cables with SC or ST connectors. As the figure shows, T3 CSU-DSUs can be built into the WAN router. Built-in T3 CSU-DSUs use HSI to interface with the WAN router, but they do not require an external HSI cable or connector. The connection between the built-in CSU-DSU and the T3 wall jack is identical to a standalone router, either coaxial or fiber optic cable and connectors. E3 WAN connections are based on the ITU-T G.703 specification and use the E3 signaling specification defined by the SEPT hierarchy. Public carriers deliver E3 WAN connections as either a channelized or a non-channelized service. Channelized E3 delivers a total of 512 E0 channels comprised of 16 E1 channels and provides 34.368 megabits per second in nominal bandwidth. Channelized E3 uses E3 signaling, which is multiplexed in a two-step process. First, a total of 16 E1 signals are multiplexed into 4 E2 signals, each of which contains 4 E1 signals. Second, the 4 E2 signals are multiplexed into a single E3 signal. In channelized E3, the public carrier performs all multiplexing. In contrast, non-channelized E3 delivers a single E3 with no E0, E1, or E2 multiplexing. It provides 30.720 megabits per second in available bandwidth. In non-channelized E3, the subscriber is responsible for multiplexing if an application requires it. For example, a subscriber may want to multiplex an E3 WAN connection to create individual channels for a PBX and multiple point-to-point WAN connections between branch offices and a main office. Both channelized E3 and non-channelized E3 require either 75 ohm solid core RG59 coaxial cable, which is the same cable that is used for linear bus Ethernet, or fiber optic cable, which has the same specifications as the cable that is used for gigabit Ethernet for the local loop. The public carrier provides a BNC connection for coaxial cable, or an SC or ST connector for fiber optic cable. An E3 WAN connection requires a CSU-DSU on the subscriber's end of the connection. The CSU is owned and operated by the PTT and is located on the PTT's side of the DMARC. The DSU is owned by the subscriber and is installed at the subscriber's premises. You must configure the DSU to use HDB3 line encoding, which is discussed in Module 1. You must also configure the DSU for channelized or non-channelized D3, depending on which one you are implementing. Finally, you must configure the WAN routers to use a data link layer protocol that supports point-to-point connections. The default protocol is PPP, but HDLC, MP, and frame relay can also be used. As this slide shows, an E3 DSU can be a standalone device or it can be built into the WAN router. The physical connections are different for each. A standalone E3 DSU connects to the WAN router's HISI connection with an external HISI or HISI V.35 cable. As discussed earlier, HISI uses a sub-miniature 50-pin connector and provides a synchronous transmission rate of 52 megabits per second for both coaxial and fiber-based E3 WAN connections. Built-in E3 DSUs also use HISI to interface with the WAN router, but they do not require an external HISI cable or connector. Whether the DSU is a standalone device or built into the WAN router, the connection between the DSU and the E3 wall jack remains the same: a coaxial cable with a BNC connector or a fiber optic cable with SC or ST modular connectors. The DS3 WAN connection offered by Japanese PTTs is a channelized T3 connection. Based on the ANSI T1.102 and T1.107 specifications, it uses the DSX3 interface and DS3 signaling specifications defined by the DSX hierarchy. The DS3 WAN connection provides 44.736 megabits per second in nominal bandwidth. The DS3 WAN connection requires one of the following for the local loop: a 75 ohm solid core RG59 coaxial cable, or a single mode or multi-mode fiber optic cable. The DS3 WAN connection uses BNC connectors for coaxial cable and SC or ST connectors for fiber optic cable. The default protocol for the DS3 WAN connection is PPP. However, HDLC, MP, and frame relay can also be used. Like the T1 WAN connection over SONET, the DS3 WAN connection requires an add-drop multiplexer. The ADM establishes the connection and the signaling between the customer's premises and the CO. In addition, a fiber termination box is required between the coaxial or fiber optic cabling used on the customer's network and the SONET network. When a customer signs up for a leased line with the PTT, the agreement may include rental of a WAN router. However, the customer should be able to purchase and use any WAN router that supports the DS3 standard, but the customer should double-check with the PTT to ensure that WAN router is supported. Some WAN routers may also require a separate card that supports an external CSU-DSU, which is in this case an ADM. Fiber optic offers substantially higher bandwidth than copper and uses pulses of light rather than electrical signals to transmit digital WAN traffic. Fiber optic is rapidly replacing copper as the transmission medium for bandwidth-intensive applications. Although fiber infrastructure is more expensive to install, it provides significant advantages to the public carrier in terms of inter-networking operations, administration, maintenance, and provisioning, or OAM&P. Fiber optic also provides significant advantages for subscribers. In addition to providing higher transmission speeds, fiber optic is more reliable than twisted pair copper and provides superior redundancy features. Because of these advantages, fiber optic is now the transmission medium of choice for T3, E3, and other high-speed WAN connections. Fiber optic is used on both the local loop and the public carrier network. For the purposes of this course, public carrier networks that use fiber optic are called fiber optic carrier networks. There are myriad standards and proposed standards for fiber optic carrier networks. Public carriers have widely accepted some standards, but not others. The most common standards in use today are as follows. ANSI SONET standards. North America and Japan use SONET standards ANSI T1.105 and T1.119 specifications. These regions also use Telcordia GR253 core, common generic criteria for SONET transport systems. ITU-T SDH standards. ITU-T and ANSI cooperatively developed SDH to ensure compatibility and to enable SONET and SDH carrier networks to exchange data. Regions outside of North America and Japan use the ITU-T G.707, 781, 782, 783, and 803 standards. OC1 standards. SONET uses the Synchronous Transport Signal, or STS specification to convert copper carrier electrical signals into optical signals. STS1 serves as the base multiple for all STS signal levels in the SONET hierarchy. After an STS1 electrical signal is converted into an optical signal, it becomes an optical carrier 1, or OC1. OCX standards. OC1 serves as the base multiple in the optical carrier X or OSX hierarchy for SONET-based carrier networks. OC1 provisions a 51.840 megabits per second channel with 50.112 megabits per second in available bandwidth. As is the case with DS0 in copper-based carriers, OC1 is the common channel used to multiplex higher bandwidth carriers in the OCX hierarchy. Like SONET, SDH uses OC1 as the base multiple in the SDH hierarchy. SDH uses synchronous transmission mode, or STM designators, rather than OCX designators to describe its optical signal hierarchy. STM1 specifies the electrical and optical signaling specifications for an SDH carrier that is equivalent to SONET OC3. Unlike SONET, SDH does not use STS, nor does it define any electrical to optical signal conversion specifications or interfaces beyond STM1 carriers. In other words, all SDH carriers above STM1 are pure optical carriers. Both SONET and SDH are capable of delivering channelized and unchannelized carrier services. Channelized SONET and SDH carriers are provisioned and use OC1 as the base multiple for higher bandwidth signal levels. For example, channelized OC3 and STM1 both contain 3 OC1 channels. In unchannelized or concatenated SONET and SDH carriers, the entire line rate is available for payload transport, and all OAM and P functions are performed out of band. In unchannelized SONET and SDH, the public carrier does not provide any multiplexing to the subscriber. T and E carrier aggregation. T and E carrier systems use a master clock signal to synchronize signal transport between the end nodes of a WAN connection. This creates issues during aggregation because public carriers may use different master clock signals. These slight variances or phase shifts must be removed prior to aggregation and transport in optical carriers. To accomplish this, SONET and SDH carriers use an asynchronous signaling method based on the plesiochronous digital hierarchy, or PDH. PDH provides backwards compatibility between SONET and SDH fiber carriers and existing copper-based T and E carriers. PDH aggregates T and E carrier lines onto SONET and SDH carriers in T1 and E1 base multiples, respectively. PDH uses bit stuffing to compensate for phase shifts among multiple synchronous input signals and provides synchronous-like signal transport without using a master clock signal. To accomplish this, SONET and SDH carriers operate at slightly higher transmission rates than the composite multiplex T and E carrier signals they carry. The additional bandwidth provides dummy bits that are used to compensate for timing differences between the T and E carrier tributaries. Fiber optic WAN router connections use the same media and connectors that are used in gigabit Ethernet applications. These include multimode fiber, 50 micron and 62.5 micron, single-mode fiber, 8.3 micron, SC and ST connectors. As this slide shows, a single-strand fiber optic cable consists of a fiber strand surrounded by a gel buffer that prevents signal loss. A strength member surrounds the gel buffer and protects the fiber strand against breakage, and a protective jacket encases the entire assembly and provides further protection against breakage. Two single-strand fiber optic cables, transmit and receive, are terminated with an SC or ST connector that completes the assembly and provides the physical connection to fiber optic equipment. The optical interface on the equipment being installed determines which type of fiber cable, single mode or multimode, and the diameter of multimode cable that can be used. Multimode fiber. Multimode fibers are made of thin glass strands that carry light signals simultaneously in two specific windows or wavelength sizes measured in nanometers. The most common multimode fiber used in optical data networks is 62.5 micron, which carries signals in 850 nanometer and 1300 nanometer windows, both of which provide 500 megabits per second in bandwidth. Therefore, a multimode fiber strand provides 1 gigabit per second in total bandwidth. Multimode fiber is commonly used in gigabit Ethernet and WAN router installations because its relatively large diameter makes connector attachments or termination easier than single-mode fiber. However, the relatively large diameter of multimode fiber causes signal dispersion, which limits its transmission distance to 1 kilometer or 3,280 feet. Single-mode fiber. To reduce signal dispersion, single-mode fiber is made of extremely thin glass strands measuring only 8 microns in diameter. Single-mode also has two signaling windows, 1300 nanometer and 1550 nanometer. Single-mode fiber provides multi-gigabit bandwidth capacity with the actual bandwidth determined by the equipment used. For example, current high-end carrier backbone installations run in the 40 gigabits per second range, but tests have shown that single-mode can carry data at 100 gigabits per second. Single-mode fiber is so small that you cannot see it without a microscope. Therefore, it is more expensive to work with and much more difficult to terminate than multimode fiber. However, single-mode fiber provides a signal transmission range of 3,000 miles and beyond because of its vastly reduced signal dispersion characteristics. Fiber connectors. Fiber optic WAN connections use the same ST and SC fiber connectors that are used for gigabit Ethernet. ST and SC connectors are available in epoxy and crimp varieties. In this module, you learned the following. T, E, and J carrier lines provide point-to-point connections, a permanent physical path, and fixed bandwidth. The local loop for carrier lines includes CSU-DSU, a network interface unit or smart jack, and repeaters. WAN routers offer capabilities such as a built-in multiplexer, a built-in CSU-DSU, security, and RMON. Examples of the different types of T, E, and J carrier WAN connections available include the following. In the United States and Canada, T1 with a transmission rate of 1.544 megabits per second, and T3 with a transmission rate of 44.736 megabits per second. In Europe, Australia, and Asia, except for Japan, E1 with a transmission rate of 2.048 megabits per second, and E3 with a transmission rate of 34.368 megabits per second. In Japan, T1 WAN connection over SONET with a transmission speed of 1.544 megabits per second, and DS3 WAN connection over SONET with a transmission speed of 44.736 megabits per second. Fiber optic networks provide substantially higher bandwidth. They use optical signaling and multimode and single-mode fiber optic cables.